So welcome everybody in the lecture hall. Welcome everybody joining us on Zoom. Welcome everybody watching us from the future. So I'm going to continue and finish actually this part on views and indices, and then we'll start discussing data cubes. So you remember that the goal of the indices is to accelerate the queries. So if you don't have any indices, it might take forever to have a query that looks for a record on a table that has 1 billion records. And for this, we have something that works like a charm, which is called an index, which is an additional structure that, in addition to the table, besides the table, you add an additional structure that is optimized for very quickly looking up the records. We saw that there are two basic kinds of indices. Of course, there's a few more, but the basic ones, hash indices and B+3 indices. Hash indices are really good to locate exact values when you're looking for a very specific value. It's this magical smoothie mixer machine that we put everything into. We get a hash, and that allows us to instantly find the values. And the other one is the B+3, which has the advantage of supporting ranges, intervals, because it's a tree structure that maintains a sorted list of all of the values. And in fact, this is very similar, as I told you, to the pages you have at the end of a book, where you have the alphabetical list of words that you can look up, and then it gives you the pages. And the analogy with the book is also good, because in a book, you see that it has extra costs, because you need these extra pages and the extra ink to pay to add the index at the end. It's exactly the same thing with a relational database. You need extra disk space, extra memory in order to have the index. And in exchange for this, you get very fast queries. Now, one of the take-home messages of this course is that you would use a database management system like PostgreSQL so that it does everything for you, right? So you don't have to worry about building these indices, because you just need to tell PostgreSQL to do it for you. And telling PostgreSQL is extremely easy, just like you type a query like select from where. Well, instead of that, you type an create index command. And in that case, we say that we create an index, we give it a name, so by title, but it doesn't really matter. And then I'm saying that I want to create an index on the publications table. That's the name of my table. And then in the parentheses, you specify the attributes that you want to index, in that case, title. This is going to create a B+3 index on the attributes title. So it's going to take a while. The moment you press enter, it's going to take a while. Everything is going to become slower, especially if the table is very big. If you already have millions or billions of records, then it's going to slow down the machine for a bit until this is done, right? So that's the extra cost also in CPU that you need to pay. And what it's going to do during that time is that it's going to go through the values of title and through the records and build a B+3 with all the possible values of title. Is everybody with me? Right? And that's all you need to do, just that. And after you have done that, and the system becomes well available again, and it's done, then you can start entering your queries, just like you would do before. So this is a select from where query. What kind of algebra operation does that do? A projection, an aggregation, renaming. It's a where clause, right? What does that do? Yes? A selection, exactly. That does a selection. And selections are exactly what indices are good at, right? Furthermore, it's a selection with an equality, right? So we love that with indices, a selection with an equality like this. So this query, even if the table has 1 billion records, will be extremely fast, because PostgreSQL is smart enough to notice that it's a query on title. It's the table publications, right? So the table that you see here is the same one that is indexed. Title is also the same. So PostgreSQL is smart enough to notice, hey, I have an index. I can use that to accelerate the query. So it's going to take mathematical logic. It's going to feed that into the index. What's the complexity of that? Instant, logarithmic? We have a b plus 3, right? Linear? You remember? It's logarithmic, right? Because you need to go down the tree. Hash table would be instance, but the b plus 3 is logarithmic. So in logarithmic time, it's going to go down that tree, locate the leaf in the tree corresponding to mathematical logic, follow the pointer to the records, and give you the records, which it fetches from disk, right? For whom is that clear? Right? So that's the magic. Even without knowing anything about hash indices or b plus trees, just with that simple comment, you create the index, takes a while, and then this query, without any modification, it would have worked before, but it would have been slow, and now it becomes fast. That's the magic of a database management system. Here's another one. So this is fast, everything is fast. Now, what about this one? So here I created an index on the year. So that's a different one. I imagine I did not do this, right? On title, I did not create an index on title, but instead I created an index on the year. And now I have a query where my predicate here, the selection predicate, is a conjunction. It's an and. The year is this, and the title is this. Who thinks, well, the answer is on the side. I'm so silly, but who thinks that this is going to be a bit faster than it was without the index? Right? It will, because what's going to happen is that, again, PostgreSQL sees, okay, I have a filtering query, a selection on year and title, but I have an index on year. It's right there. I built it. So it's going to use the index, feed the 1905 into the index. It will get a lot of records, of course, because this is the year 1905, but it's going to be less records than the entire table because it's only the records for the year 1905. What does it do with that? Well, it just filters that in memory. It has to go through the records and then take the ones with the theory of relativity. And that's not going to be with the index, but it's only doing that on what came out of the index, only on the year 1905. So you see, it's looking at less records because it already took a subset of the records. Who is still with me? Right, very good. This one is not going to be faster. It will work, but it will be very slow if I build only the index that you see on the top. Why is that? On Zoom too, you can send your answers. I will make Marcin a co-host too. So why, if I create only the index that you see on the top, why is that query going to be slow? Exactly, the index is on year. I have built a b plus 3 on year, but the selection predicate that I have here is on title. So the index is totally useless for that, right? I don't have an index on title. I could, of course, build one, right? But then I have to wait until it's done. Okay, very good. Next one. To reselect the right window. Now, who can tell me why this query is also going to be a bit faster? It might be slow because of the number of records to output, right? Because it's going to be a larger output, but it's still going to be faster than without the index. Can anybody explain to me why that is? Yes? Mm-hmm. Yes, exactly. So I'm repeating for the people on Zoom. So the index is on year, and the query is also filtering on year. But now it's just it's not an equality; it's greater than. But the good news is we have a b plus 3 index, not a hash index. If it were a hash index, you could forget about it. But a b plus 3 supports that. So what it does in the b plus 3 is that it's going to take 1905. In logarithmic time, it will locate the leaf that says 1905. But because it's a b plus 3, once it has located this, it will take, you remember this highway that we have on the leaves. Like once you are on a leaf, you can take the highway and find all of them on the right or on the left. You can navigate left and right. So greater than 1905, it's going to just take the highway to the right of 1905, skipping 1905 because it's strictly greater. So it's starting 1906 and so on. And it's going to efficiently, linearly go over all the values higher than 1906, equal and higher than 1906, and output all the records, right? Who is still with me? Right, so this is the magic. It also supports ranges. So we have a filtering predicate with something that is indexed and with a range query. So that is absolutely possible with an index. So it's going to be faster. And I said faster and not just fast because it's an interval query and there's probably going to be a lot of publication after 1905, right? So you still need to output them and that takes time. There is this general rule in computer science when the students in computer science learn about algorithms and data structures that an algorithm cannot be faster than the size of what it outputs, right? Because at the very least, the algorithm has to output what it outputs. Okay. Next one. This one is going to be faster too, and that's another example of conjunction. So I'm looking at two criteria, the year and the author. The year is indexed, the author is not indexed. So what's happening is that I'm going to use the index for the year. Probably 1905, maybe you get half of the table. Like one half of the table before 1905, you don't get it. The other half after 1905, you get it. And then the filtering on author equals Albert Einstein is done manually. So you have to go through them one by one, but only on the half of the table that you took from the index. Who is still with me too? Right, very good. So it's just a few examples. Of course, you can index multiple columns, right? You could also have an index where you have all the years. And when the years are the same, then you sort by author, right? You've all done that in spreadsheet software or in Excel, right? You have all of the columns, you activate the filtering, and then you have these little buttons that you can sort ascending, sort descending. And then if you click on one column and then another column, that's going to be a primary sorting by the last one you clicked and a secondary sort with the second one. Who has ever done these things? You've never done that? Or you should try this in any spreadsheet software. So let me, yeah? Yes, go ahead.
First index by year, and then by author?
Absolutely. So exactly, by year and then by author. So you're going to have, for example, if you look at the leaves of the index, you're going to have what's the earliest we can go to, maybe minus 3000 and some ancient Greek authors and so on, or from the Indus Valley civilization, so the very ancient ones. And then you have 1 year, and then you have all the authors by alphabetical order. After you've reached Z, or whatever alphabet was used back then you get to the next year, and again you have all the authors sorted, and then the next year, then you have 1905, A, B, C, D all the way to Z, 1906, A, B, C all the way to Z, 1907, and so on. So it's basically treated as if the value you're indexing is actually a pair, you're indexing a pair, and we call that a lexicographic order in the sense that you first sort by year and then by author, right? If you had author year, it would be the other way around. Then you would have the letter A all the years one by one, then the letter B all the years one by one, and so on, right? But here we say year author, so it's first the year and then the author, right? Do you visualize the B3 index, B+3 index like this? Okay. So that's something very nice that we can do with the B+3 index, that we can have multiple keys, very convenient. And so that's going to be very helpful for queries that filter by year and author. Let's say an equality, you find it instantly. Now, bonus question. Do you see that this index is also going to be useful for queries that only look for a specific year? Do you see why? If my query, it's indexed by year and author, but my query only says, let's say, the year 2024. Who sees why the index is useful? Yes? Exactly. Since it's first order by year and by author, you have to imagine in the index, you're going to have 2024A, 2024B, 2024Z. So you just take the interval. Yes? That is correct. It only works if you query specifically for the year. It will not work if you query only for the author. Because imagine you query for Einstein, let's say. You would have to look manually in the index for the 1891 Einstein, 1892 Einstein. They are not contiguous, right? They will be once every year because it's the second key on the index. So this is something that is indeed very important. It has to be the left, coming from the left, if you want to query efficiently. Who is with me? Right? That's already kind of advanced, but many people are not aware of this. And for example, you have people, the mistake they make is they create an index by year and author, and some people will also create an index just by year. And this is actually a waste of space because the second index is useless because you can already use the first one. And that's a very common mistake that you found in some companies, that they are wasting disk space by having indices that are redundant in this way, right? That's already advanced, of course, for me to tell you that. Okay. So of course, these were B plus trees, but if you want a hash index, you just, if you want a hash index, you just say using hash, right? And that's it. So it's just slightly modifying the syntax using hash, and then you specify the field you want, then you get a hash index. That, of course, will only work for the equality. If you try greater than, greater than, lower than, that's not going to accelerate because a hash index only works for equality, just because it spreads all over the place in no particular order. The slide before that I jumped because I wanted to talk about the hash was this one, a B plus tree sorts the values, and you can also specify how. You can say descending, ascending, so that also you can control. So for example, that's creating an index, a B plus tree index on year, descending. It's going to start at the left, on the left of the index with 2025 and then 2024, like descending all the way to the antiquity. And nulls first even says that you start with the nulls and then 2025 and so on. You have a question?
Yeah. So in terms of speed, indexing on year is the same as indexing on year and author, assuming that we query only on year.
Yes, if imagine that here you have a query that specifically asks for an equality, so year equals blah, 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 the index that you see on the screen will be very useful. That's going to be just as fast. The only difference with an index by year or year and author is just that this one will have more leaves because there will be a leaf for each, so we still have in blocks, but there will be an entry for every author. But since you have what I call the highway on the leaves, you can very efficiently traverse that. So it's going to be mostly almost as fast, whichever you use. Does it answer your question?
Yeah, thank you.
All right. Okay.
Another one.
Yes, go ahead.
But the more indexes, the more it slows down the writes, right? Occupies disk space.
Yes, absolutely. That is a very good point. So let me summarize the costs of having an index because there's a lot of costs. There's 3 costs actually, most of them. The first cost is the disk space and the memory space. It just takes space to have the structure. The second cost is during building the index. The moment you enter that and press return, you might have to wait for a couple of hours if the table is very big. So there's a cost that you pay at the moment you create it. And what you mentioned on Zoom is a third cost. It's that once you have created an index, you have asked PostgreSQL to create an index, and then you start modifying the data that is already indexed. So you start changing the values. Imagine you modify a year, you modify an author. In the previous one, you modified an author. The index has to be modified too, right? And that means that every index you create means that the writes are more expensive. The updates to the tables are more expensive. If you create 10 indices, then it will be 10 times as expensive. If you create 100 indices, you shouldn't, by the way, create 100 indices, but if you create 100 indices, then you can imagine how slow every update is going to be because you need to update 100 different indices, right? Who has the intuition of that, right? So memory space, disk space, immediate cost when you create it, and later costs when you update the data. So this is a very good remark as well. So this is why you need to create your indices with parsimony. You need to really be very careful and aware of the costs that it has. So when you create your indices, typically in a company, it's done in a database where a lot of people are going to query. So what do? You try to understand what people are querying, and you are going to try to create the indices that corresponds to, let's say, 80% of the cases or 90% of the cases, so that most queries will be faster, and you prioritize the indices that correspond to the more popular queries, right? Okay. Yes? Oh, right here, yeah. Oh, it just controls the kind of queries you have. So in fact, if you just do a single one like this, that doesn't change much because you can revert. But if you have multiple attributes like here, and you sort ascending, descending, then it makes a difference. Oh, for an equality, it doesn't make a difference. Yeah, but for a range, it might make a difference. Yeah, I don't have an example that comes to my mind when it makes a difference for a specific query, but basically, physically, that controls the order in which the B plus tree is going to arrange the values. Yeah. Oh, I can give you an example actually. When you have a B plus tree, you can also use it to accelerate order by queries. Imagine that now you have an order by query that says order by year, and you happen to already have an index that has the years ordered. Do you see that now, you know, by any chance, does anybody know the most efficient generic sort algorithm, what the complexity is? Yes? N log n. Who knew that? Who did not know that? It's not everybody knows that. So basically, sorting things, imagine you have a list of 1 billion values and you want to sort it. Computer scientists have been trying for decades to find the more and more efficient ways to do that, right? Who heard of bubble sort? Right, so bubble sort is when you have a deck of cards and you want to sort, you might have been there, right? You need to sort the deck of cards. So bubble sort is very naive. You just swap 2 by 2 the cards, you go through the deck, and whenever they are in the incorrect order, you swap them in pairs. Very inefficient. It's quadratic, n squared. N log n is the complexity that is the best one for sorting. I have a funny anecdote about this, is that I don't remember if it was 2008 or 2012 during the American presidential elections, but Barack Obama was visiting the Silicon Valley, and he was visiting the entrepreneurs there. And they asked him in the middle of the interview, just out of the blue, what kind of sort algorithm would you use, Mr. Obama? And he answered, and that made everybody laugh, I would not use bubble sort. Right? I don't know if somebody told him or if he just had the knowledge, but this was quite funny. But anyway, this is the take-home message. Do not use bubble sort, very efficient. And the best sorting algorithms are n log n. And so what I'm coming at is that n log n is slower than just n. N would be linear. But when you have here an index that already has the years sorted, then in order to get the sorted table, you only need to go linearly through each one of the years in the index, and then you get better than n log n, you get n, O of n. Right? For whom does that make sense? right? It's like I give you an already sorted deck of cards and I ask you to sort it. Well, you just go through them and that's it. You don't even need to do any efforts, right? So that would be an example of where the order actually matters, because if you sort by A ascending, and you do order by A ascending, B descending, then that's not going to work. That would be a concrete example to answer your question, right? Okay, did I answer your question? Yeah, all right, okay. That was, by the way, what I said in the last 5 minutes is advanced. All right, that's so don't worry if that sounded a bit complex. Okay. And then this is just repeating what I said, because that's the question you asked on Zoom, right? When you have no index, writing is fast, of course, because you just write what you want to modify, but reading is slow. And when you start adding indices, then reads become faster, if the query, of course, corresponds to the index. But the writes become slower, because every time you modify something, you need to update the index. Okay? Everybody agree on this? Okay. That was actually the last slide, and here I had my 500 interval server error on the Menti, but maybe it works now because that was the same thing that Zoom and Menti had earlier. So I will still see if right now, if I just refresh, that will suddenly start working again. Reload. Yeah, it seems so. I might need to still reselect. I'm going to reselect the screen here. Okay. So hopefully that's going to work. So this is a question on the entire views and indices lecture. Like, do you get what an index is doing, why it accelerates queries, the difference between a hash index, a B+3 index, and do you understand on the very high level when your queries will be faster given what index? Like, do you have the intuition for that?
Maybe in the meantime, we have a question on Zoom.
Yes.
What is meant by write? What is included in write? This is about faster write and the compromises to make slide.
So what I mean is any query that modifies the data. An insertion of a new record, a deletion of a record, changing the value in a record, so all of that. Anything that modifies the table, basically. Change of schema too. If you alter the schema, that's going to be slow in any case. Okay. So I got a majority above 80%, so that's very good news. Nobody less than half. So what I would say is, as always, if anything is unclear, you can drop us an email to your TA, to me. Don't hesitate to ask. We'll be very, very happy to explain again, right? What I also recommend is to read the textbook that I gave you the chapter, so you should read this. Yeah, hopefully it convinces you to use a database like this for your semester projects and your master's thesis, because you will notice the difference. If you're working on ETH data sets that are very large, then you will appreciate the convenience of getting instant results in your Jupyter notebook, as opposed to using Pandas, for example, or in Python, which would not have indices. Okay, so this is the end of this one. So very happy with the results that I did not lose you. So I'm going to stop the recording.